Okay. Says recording has started. Maybe I can switch off my video so that we don't eat up the bandwidth. Let me go back to the. So we'll start in a casual style, and eventually we'll build it up into the formal theory. Some of it is things you're familiar, so I think that's why I'm starting from the casual style and build it up to the more abstract. Casual here means the concrete, then we'll build it towards the abstract eventually. I will need to get your email so that you are invited to the class, and then I don't have to keep admitting you one by one. I think we can get the emails later. Now I can see we are still having people joining. Okay, can you confirm what you can see, that you can see this slide which says linear algebra for data science?
Yes. Yes.
Okay, so I can proceed. So this is just a list of a table of contents of what we'll do. It's still going to have a few extra things that are not here, but this is enough to get us started. It's quite a chunk already, so we have a lot to do before we can add more. Now, I'll start with this. You're all familiar with this Cartesian plane. Now, we sometimes refer to it as R2, where 2 is a superscript here, or it's not R squared, it's R2. And we take it to be the set of ordered pairs of real numbers. So any point in the Cartesian plane consisting of the x coordinate and the y coordinate is an element of this set R2. So we shall call these ordered pairs vectors, and instead of writing them as a row, x and y separated by a comma, we shall write them as a column instead. So we shall choose to represent our vectors as columns. There are other cases where vectors are represented as rows, but throughout our course, a vector will be assumed to be a column vector in this form. So this is not new to you. It's just the Cartesian plane, because any of these vectors can simply be represented as a point on the Cartesian plane. So this can be built up. Here we have only 2. We can grow it further and put some structure on the set. So once you have a set, normally you can put some algebraic structure on it. In this case, we are going to define 2 operations. The first one is addition. So you can pick 2 of the vectors in R2 and add them. Remember, we are writing them as column vectors. And if the first vector is this 1, 2, the second vector is 3, 4, you can add them. And how you add them is simply add the components that are in the same position. So this 1 is in the first position, 3 is in the first position, you add them up and you get 4. You add 2 to 4 and you get 6. So you can add 2 vectors in R2 like that. There's one more example here. We add 215 to 08 and you get your answer as 2 plus 0 as the first entry and 15 plus 8, which is 23 as the second entry. So that's how simple it is, this operation. This is one operation you will use a lot as we go along. I think there's some people in the lobby. Let me admit them, then we can proceed. I think after the class, I will ask Elisha to assist in getting the email so that I can invite all of you. So here you can add any two vectors. This can apply to any pair of vectors that you pick, and you can extend it to even 3 or more vectors if you so wish. That's possible. You can keep adding as many as possible in the same fashion. So the other operation that we're going to, the algebraic operation that we'll add here is scalar multiplication. You multiply a vector by a number. Scalar here simply means a number. And in our case, the number will be a real number. So for instance, if you have the vector 4, 9, we can multiply it by 2. And what happens in this case, you simply multiply each component in the vector by the scalar. So 4 will be multiplied by 2 as well as 9, and the result will be 8, 18. We have a second example here where the number we are multiplying with is a fraction, and we end up with the result here 7.5 and 12. You're multiplying 1 1/2 by this vector 15, 24. And each of them is multiplied by 1/2, and the result is 7.5, the first in the first slot, and 12 in the second slot. So this operation is called scalar multiplication. And the previous one, we called it vector addition. So keep track of this. These are important things to note down. So this looks trivial, but it's really important that you write things down as we go along. It will make your revision better. Don't just stay at the screen. You probably will forget most of the things after the class is over. And if you have them written down in a notebook, you'll remember. You'll pay more attention to them and you will remember better. So we've done vector addition and scalar multiplication as well. But that was just in R2. Now it's possible to extend this to a larger space, as we shall see shortly. But we can point out some of the special vectors that appear. So the vector consisting of the where all the entries are 0 is called a 0 vector, and often we'll denote it by a bold 0. And of course, if you add this 0 vector to any other vector, it doesn't change. The 0 vector does not change the vector because you're adding 0 to each component, so none of the components will change. The other special vector that we can talk of is the negative of a vector. So if you have a vector v, its negative is denoted by negative v, and it's simply negative v is a vector which when added to v will give you the 0 vector. So what this simply means is you multiply what is in v by -1 to get negative v. So the same ideas we worked on can be extended to 3-dimensional Euclidean space, where you have 3 entries in your vector, x, y, and z. And now this one becomes a bit harder to draw, but still possible to draw. It's harder to draw because you have many possible directions you can view space. So depending on which side you're viewing, whatever you're drawing might look different. So there are several views you can use to draw this. But we want to build it up to the point where we no longer worry about drawing. And just think of the algebra instead. So here are some examples of vectors in R3. So in R3, again, addition, you can extend that addition and scalar multiplication as follows. You simply add vectors by adding components in the corresponding positions. So 1, 3, 7, and 7, 5, 10. If you add those two vectors, the corresponding values for the first slot are 1 plus 7, which is 8, 3 plus 5 for the second one, which is also 8, and 7 plus 10 for the third one, which is still 17. You can still do scalar multiplication the same way. In this case, we are multiplying this vector consisting of 1.5, 0.2, and 9 as the entries, and multiply that by 2, means you multiply everything in here by 2, and the result is 3, 0.4, and 18. So again, if you combine this set R3 together with these two operations of vector addition and scalar multiplication, will also be a vector space. So now I'm using the term vector space. We have not defined what it is, but you just have to accept it for now. We shall define it shortly. It's a rather abstract concept, but it's sufficient for this. This is it's sufficient enough for us to call this a vector space. It is true anyway and can be checked, but for now we'll just be happy to call it a vector space before we give the formal definition of a vector space. Let's check. I think there's someone trying to join. I think some people are being knocked out and returned. Maybe the internet is a bit shaky. So if you have any questions, you simply put on your microphone and ask. So far, I don't think this should be new to anyone, or at least most of you. So instead of working with 2 or 3 components in the vector, we can work with a finite number. In this case, n is just a positive integer. You can have a list of numbers, x1 up to xn, and put them in this form. And this set of, they're called n tuples, are the elements of Rn. And each entry, each xi is a real number. Each entry in this n tuple is a real number. And they define this set Rn. So any element in Rn would look like this, where every entry is a real number. So you can add 2 vectors, x and y in Rn, again by simply adding the corresponding components. So this is a more general definition of the addition of vectors, where you're not limited by the value of n. This will work for any value of n. We also define scalar multiplication, where the scalar is alpha, a real number, and x is a vector in Rn. If you multiply the vector by the scalar, it means you simply multiply all the entries in the vector by that scalar. So this Rn, again, is a vector space under these operations. So we call it a vector space over the real numbers because we are multiplying the scalars we are using to multiply the vectors are real numbers. So if you use scalars from a different field, for instance, complex numbers, then we would say it is a vector space over the complex numbers, but we are not interested in the complex numbers for now. The real numbers will keep us busy, sufficiently busy until later when we may need complex numbers later. So are there any questions so far? So maybe one other thing I will point out, I've written these vectors here as rows, but we shall be representing them as column vectors. As we proceed, we will not be writing them as as rows, but as columns. So this, in some sense, this is not the notation we shall be using, it shall be columns. So here we can now make a formal definition of a vector space. So a vector space requires the following things. You need a set. In this case, our set will be Rn, and you need a field. In this case, our field is still R, and that means our scalars will be real numbers. And then this set, you define addition on it. You can add two vectors, and the addition requires that if you add two vectors, you should get another vector in the same set. So you need there's some brackets missing here. You need the associative property. So we need brackets on the first pair of vectors, u plus v, which is here. But so if you move the brackets to v plus w on this first left-hand side of this second property, you still be equal to putting the brackets on the first two and adding the third. So where you put the brackets doesn't matter, and that's the associativity property. So this addition operation should satisfy this associativity for any three vectors that you pick from Rn. Then if you add, there's a zero vector which consists of all entries equal to zero. If you add it to any other vector, it doesn't change. There's a negative of a vector, which when added to a vector will give you zero. The order in which you add the vectors does not matter. So u plus v should be the same as v plus u. This is the commutative property. And scalar multiplication is also defined so that if you multiply any vector by the scalar, you still get another vector in the same Rn. And then the distributive property, you can multiply the sum of two vectors by a scalar, and that scalar can be distributed across the two vectors. On the other hand, also, you can add two scalars and multiply by a vector. And so alpha and beta are scalars. If you add them in brackets and multiply by vector, it's the same as alpha v plus beta v. So you can split them like this, still get the same answer. Also, you can multiply two scalars by a vector, and it's the same as first multiplying the vector by the scalar beta, and then followed by alpha. It doesn't matter where you put the brackets, you'll get the same result. And if you multiply the vector by 1, you should get the same vector. So these properties, you don't need to worry about them. But this is what, for now, we will not need to use all these properties. The most important properties we will be using are this property of scalar multiplication and vector addition. The rest will sort of fall in place as we proceed. A lot of them are natural, so they will not give you a lot of trouble as we use them. But you don't need to cram all these properties. They're just there to show you the abstract definition of vector space. Now, there are many other types of vector spaces you can have. Given the time constraints, I don't think we will do any other vector space other than Rn. I can provide material for those who wish to delve deeper into other vector spaces. I can provide material. I actually did provide some books to Elisha, which cover they cover this in more depth. So that anyone interested in going deeper into vector spaces, you can read on your own. You're free to ask questions as well. When you read and you find something that doesn't make sense, you can always ask. So I don't know if there are any questions so far up to that point. So as I said, you should be making short notes as we proceed. Don't just stare at the screen. You will not follow. You will have trouble. So the next thing we'll see is how do we combine these two operations together, the vector addition and scalar multiplication? You can use them to construct new vectors, which are what we call linear combinations. So we start by illustrating this idea of linear combination. So, for instance, if I have these vectors u, v, and w from R3, we can obtain linear combinations of the vectors as follows. So linear combinations is simply multiplying a vector, each of the vectors in your set by a scalar and adding them. So this first set is a linear combination of u and v. You just multiply u by 2 and multiply 3 by v and then add them. So the result is what we call this. Now it means 5, 8, 21 is just a linear combination of these two vectors u and v. They are listed here, 1, 1, 0 and 1, 3, 7 as the vectors, multiplying the first one by 2 and the second one by 3 and adding them. So this is an example of a linear combination of two vectors. So what exactly is it? It's just adding multiples of vectors together. So this is a multiple of u and this is a multiple of v, and added together, that's an example of a linear combination. So you're not limited to two vectors. You can add as many as you wish. Here we have u, v, and w, a linear combination of the three vectors. So 3u minus v plus 2w gives us 4, 0, negative 5. So it's important that you double check this in your own time. I hope the calculations are correct, but it's a simple calculations that you should be able to convince yourself that they are true. If not, you should be able to find the error. They are not complicated. So, but what is more important now here is understanding a linear combination of vectors. Simply get scalar multiples of the vectors and then add them up. So here we have the scalar multiple of u, 3. Here is a scalar multiple of v, basically negative 1 times v. That's a scalar multiple, and this is 2w. And then their sum is a linear combination of the three vectors. You can put any numbers you wish. I just use these numbers as examples, but you can use any scalars you wish to create new linear combinations of the same vectors. So that's precisely what this says. When you change the scalars, you get new linear combinations. So this is the general definition now. In general, if you have R vectors, U1, U2 up to UR, in this case, we choose them to be vectors in Rn. Then we have another set of R scalars, which we label as alpha 1 up to alpha R. Then we should be able to construct a linear combination as follows. Simply multiply each vector by the corresponding scalar, and then you add them. So this is now a linear combination of the vectors U1, U2, all the way up to UR. Are we together? So these are the building blocks. It's really important that you catch these building blocks because we are going to refer to them casually as we go along. They'll be used a lot later. Now it's important that you catch these building blocks. So I think there are no questions on linear combinations.
I have a question.
Yes.
Okay, my question is, when we were learning about the Cartesian plane, the XY plane, we were taught that the X represents the independent variable while the Y represents the dependent. What about in this case where we have a vector space of spanning to 3, 4, and those like numbers? How do we know that which?
We are not working with equations. When you're working with equations is when you worry about dependent or independent variables. In this case, there's no dependent or independent variables. We're just working with points in the space.
Okay.
So unless you're working with equations, That's when you will need to know which one is dependent and which one is independent. We are not working the questions at all here. That
Okay.
might come later. So your question is answered?
Yes, sure.
Yes. So we for now forget about dependent or independent. Here they're just points. You're thinking of points in a vector space, or or other vectors in a vector space. And then we get their linear combination. We don't care about which one is dependent or independent for now. So here is another concept that we will find useful. We talk of linearly dependent vectors. So two vectors U and V are said to be linearly dependent if one of them can be written as a multiple of the other. So for example, if you have the two vectors U and V, if you can write U as a multiple of V, lambda here is just a number, it's a real number. So if I multiply some real number by V and I get U, I can say that the two vectors U and V are linearly dependent. Right? So for example, we have this vector in R2, 4, 6, and the second vector V, 2, 3, both of them in R2. And we observe that we can write U as 2 multiplied by V. You can double check that it is true. If you multiply V by 2, you will get U. So U and V are said to be linearly dependent because now I am able to obtain U as a multiple of V. So observe here that this is true. This definition is a true for only a pair of vectors. We can extend this to more than two vectors, and we'll do that in a short while. But anytime you have two vectors, it's quite easy to check whether one is whether the pair is linearly dependent or not. If they're linearly dependent, it should be just easy to check that one is a multiple of the other. So you could also write V as a multiple of U, because what you do in this case is multiply by a half, U by a half to get V. So it works in both directions. So when you have two vectors and one can be written as a multiple of the other, we claim that the two vectors are linearly dependent. So
Hello,
if you have,
Daktari. There are people
yes,
waiting to be let in. They're communicating in the class group.
okay. On the all latecomers. We've admitted them.
Thank you.
So this describes linear dependence for two vectors only. If you have more than two vectors, you can define linear dependence as follows: that if you have a set of 3 or more vectors, we say that that set is linearly dependent, not independent. This is not right. It's linearly dependent. This is a typo. So make sure you note that down, that this is supposed to be linearly dependent if one of the vectors can be written as a linear combination of the other vectors in the set. So anytime you have that, then we can say that that set of vectors is linearly dependent. I think I'll correct this and send later on I'll go through them line by line and try to fix any errors. So here we are looking at an example where we have a set of 3 vectors. In this case, we have picked vectors in R3.
Thank you. You're well also.
Someone's microphone is on and they're speaking. I think there was someone to be admitted. I've admitted them now. So we say that a set of 3 or more vectors will be said to be linearly dependent if one of them can be written as a linear combination of the remaining vectors in the set. So in this case, we have 3 vectors, u, v, and w. If you pick w, you can check that it can be written as a linear combination of u and v, which is 2u plus v. Similarly, v can be written as a linear combination of w and u can also be written as a linear combination of w and v. So this set of vectors, u, v, and w, will be said to be linearly dependent. Because if you pick any one of them, you'll be able to write it as a linear combination of the other remaining vectors. I think there's more people trying to join again. Should have gotten the class rep's email so that he assists in admitting. So I believe this is clear. If anytime you're given a set of 3 vectors in R3, it should be okay. In this case, it's easy to check, but we shall learn how to confirm whether a given set of vectors is linearly independent or dependent later on. For now, you just need to know the definitions, and later on we shall figure out how, when given a set of vectors, how do you determine that they are linearly dependent? So in general, now if we get the formal definition of linear dependence, if you have R vectors in Rn, so now in any general Euclidean space, Rn, or the n-dimensional Euclidean space, we'll say that these R vectors are linearly dependent if we can find a corresponding set of scalars, R of them as well, and such that at least some of these should not be 0. We must have some non-zero scalars in that set. So that's why we say not all 0. So some of them should not be 0. There should be some scalars which are different from 0, such that this linear combination equals 0. So if you can find these scalars, alpha 1, alpha 2, up to alpha r, such that this linear combination of all these vectors, u1 up to ur, equals 0, the 0 vector. Remember, when you add a vector, you must get a vector. So this bold 0 here is not a number, it's a vector. It's a vector in Rn whose components are all equal to 0. So if this happens, we say that these vectors u1 up to ur are linearly dependent. So this generalizes the idea of linear dependence to an arbitrary set of vectors in Rn. Not just arbitrary, but finite also. Arbitrary finite set in Rn. Okay, there are no questions on this one?
I have a question.
Proceed.
From what you have showed us. For example, if we said vector u is 4, 6, and vector v is 2, 3, since we can express u in terms of v, we have said that is those 2 vectors are linearly dependent.
Just a minute. Let's start again. I'm going to use the screen here. So what are you saying? You're saying we pick one vector, u is equal to?
U is 4, 6.
You can see what I'm writing, eh?
Yes.
Okay. So u is
vector,
4, 6.
V is 2, 3.
V is 2, 3.
Okay, so these two vectors are linearly dependent because U can be expressed in terms of V. That is, U is equals to 2V. Now, from the general definition that you've given us from the last slide that we've had, you've said if you add those linearly dependent vectors, they need to give you the zero vector. But in this case, if we add UV, it doesn't give us the zero vector.
So you can get zero as follows.
U
minus
2V.
2V. So the definition says you should be able to find scalars which make this equation true. Here, 0 is a zero vector. Maybe if I write by hand, I can't differentiate between bold and ordinary font. So I'll use a bar here to represent a vector. Because when writing by hand, you can't differentiate bold and. So the bar up here means this is a zero vector. So you don't think of it as a number. So what it says is the following. If you have a set of vectors, U1 up to UR, if you can find scalars alpha 1 up to U alpha R, such that alpha 1 multiplied by U1. So as long as you can find such scalars that satisfy this equation, alpha R UR, UR are vectors. So maybe I should also put bars here so that such that this gives us a zero vector. Again, I'll put a bar. If you can find such scalars that gives us this linear combination as zero, then we'll say these vectors U1 up to UR are linearly dependent. So in this case, we have two vectors, 4, 6 and 2, 3. We have found two scalars, 1 and -2. Still gotten 0. So we are not, these scalars you can find is not unique. The solution to such is not unique because you can also have this half V or minus half V plus U will still give us 0. Is that correct?
Yes.
So the scalars that you use are not fixed. You can have many different possibilities. But as long as you can get such scalars that satisfy this equation, where this linear combination gives you the zero vector, then we'll say V and U are linearly dependent. And this is true now even for the case where you have more than two vectors, 3 or more. So that's what we have generalized here. So this one here, yes.
Maybe to clarify.
So don't worry, for now, don't worry about how you find the scalars. Just focus on the definition.
Okay, maybe just to clarify the definition. So it follows, therefore, that if we are able to prove that one vector can be expressed in terms of the other, and also that those two vectors, we find a scalar that can make it 0. Therefore, those two conditions need to be satisfied so that we say the vectors are linearly dependent.
This condition is equivalent to the other one. So if this one is satisfied, you should be able to see that they're equivalent. You just need to prove this one or the other one. So if this one is satisfied, if once this condition is satisfied, then the other one is also satisfied because I can move one vector to the right-hand side, make it negative, right? So I can have, suppose I'm working with only 3, alpha 1, U1, plus alpha 2, U2, plus alpha 3, U3, all these equal to 0, right? So this is a definition. If this happens, then U1, U2, and U3 are linearly dependent. So I'm assuming now we're working with only 3 vectors. Now, once I write it like this, I can choose to add alpha 2, then I have U2, and then I can choose to send this alpha 3 to the right-hand side, in which case it will be negative alpha 3, U3. Is that correct?
Yes.
Then I can divide both sides by this negative alpha 3. So what now, here I will have alpha 1 over negative alpha 3, U1 plus alpha 2, again divided by negative alpha 3. And this time multiplied by U2, this will be equal to U3. So I started from this definition, and we've gone back to the earlier one where we said one of the vectors can be written as a linear combination of the remaining ones. Now, if you want to understand all this, we will have to go deep into the theory. So this definition, for now, what I want you to take away from this definition where you have a linear combination that gives you 0 is equivalent to the definition which says that one of the vectors is a linear combination, is a linear combination of the remaining ones. So any of them will work. They're equivalent. You don't need to show both. You can move from this one back to this one, and you can move from this one back to this one. They are the same thing.
Okay.
Yeah. So ideally, this is where I should have started the definition. And from this definition, we can show that it is equivalent to these other statements that we made earlier, where we say a set of vectors is linearly dependent if one of them can be written as a linear combination of remaining ones. So, and that is true for any of these vectors. You can also write, now if you push U1 to the right-hand side, now you can write U1 as a linear combination of U2 and U3, and so on until you're able to check for all of them. Any one of them can be written as a linear combination of the others. So the other thing I propose is you try to look at the textbooks I shared. They cover this, might cover this in a little more detail. If I go into a lot of detail, we probably will not go beyond the first week. There's you can spend a lot of time on this and do theorems and so on, a lot more, but I don't think we have the time. So for now, you trust the process. But you're free to ask questions, of course, but more importantly, catch this definition. Don't worry, don't overthink it. So the next concepts that we will look at, I believe we are done with that part. There are no more questions. Maswali. So the next concept we shall look at is linear independence. So we'll look at linear independence now. So in this case, we'll start again with a set of 2 vectors and build it up. So if we have a pair of vectors, it's easy to check if they're linearly independent, because that will happen if we cannot write one as a multiple of the other. So by definition, we'll say a vector, one vector on its own will be considered to be linearly independent if you consider a pair of vectors, you can check, for instance, if you have u is equal to 1, 2, and v is equal to 1, 3. This pair is linearly independent because there's no real number which can a lambda. If you cannot find a real number such that u is equal to lambda multiplied by v, we can't write u as a multiple v. This is something you can check quickly. Let's see what that means. That statement makes some assumptions, which maybe some are not able to see. So we have 1, 2, and the other one was 1, 3. So for this to be linearly independent, we need to show that it's not possible to find a number lambda such that 1, 2 will be equal to lambda multiplied by 1, 3. So we can check, how do we confirm that this is not possible? This would mean that 1 is equal to lambda, and at the same time 2 is equal to 3 lambda. So is it possible to find one number lambda that satisfies both of these equations? Because if you take lambda to be equal to 1 and substitute it in the second one, it doesn't work. So there's no solution. You can't find a number lambda which satisfies this vector equation. And in such a case, we say that these two vectors are linearly independent. So 1, 2, and 1, 3 are linearly independent. I can't write any of them as a multiple of the other. So here is another example. In R3, you have two vectors. The first one we call it Q, which is 1, 1, 0, and the second one is V, is 1, 0, 1. So again, these are linearly independent because it is not possible to find a real number alpha such that U is equal to alpha multiplied by V. Using the same idea as we had here, you can try to check that indeed this is not possible. Here, one way that you can check quickly is that if I have some number lambda which are multiplied by V to get U, then it means I should be able to multiply that number by 1 to get 0. Multiply the same number by 0 to get 1, and multiply the same number by 1 to get 1. It's not possible to get such a number. And therefore, we'll say that Q and V, in this case, are linearly independent because we can't find this number alpha. That makes sense. So we're going to extend this to a set of 3 or more vectors. So now 3 or more vectors are said to be linearly independent if none of the vectors can be expressed as a linear combination of the remaining vectors. So here is an example. We have 3 vectors, 1, 2, 3, 0, 1, 0, and 0, 0, 1. So the claim is that we want to check that they're linearly independent. So what we need to show is that it's not possible to write U1, for example, as a linear combination of U2 and U3. So we can check that as follows. So we can set up this equation and substitute the vectors with the scalars A and B here. So initially we don't know what these scalars are, but we want to check whether it's possible to find such scalars. So we label them A and B and place them in this equation. So we proceed to substitute the vectors into the equation. So we say that 1, 2, 3 is supposed to be A multiplied by 0, 1, 0 and B multiplied by 0, 0. So once you multiply this out and add, this will be A plus 0. I mean, A times 0 is 0, plus 0 gives you 0. A plus 0 again gives you A, and 0 plus 1 gives you 1. So this leads us to These are two vectors, 1, 2, 3, and 0, A1. Right? It leads us to a strange case where, two vectors are said to be equal if every corresponding component is the same. So in this case, we have 1 here and 0 at the end, which is just not possible. 1 is not equal to 0, and 3 is also not equal to 1. So this vector here is not equal to this vector. So there's no such set of numbers, A and B, which will satisfy this equation. So I cannot write this vector as a linear combination of the remaining ones, and therefore that set of 3 vectors is said to be linearly independent. So we'll look at the general definition now of linear independence. So if you have R vectors, U1 up to UR, we'll say they are linearly independent if whenever this equation is satisfied, or rather the only way that this equation, this linear combination can equal 0 is if all the scalars are 0. There's no other way you can get 0 other than when all these scalars alpha 1 up to alpha R are all 0. If the only solution to this equation here is these scalars, all the scalars being 0, then we say this set of vectors are linearly independent. So you could go back and to this example that we have. We have 1, 2, 3. So this time now we use scalars. The first, suppose we want to check that this set of vectors is linearly independent. Alpha multiplied by 1, 2, 3. Then the second alpha 2. What was the second vector? It was 0, 1, 0. And the third vector is 0, 0, 1. And we want this to be equal to the 0 vector. We want to show that the only way this can be satisfied is if all these scalars are 0. If you can show that, then we'll have established that these 3 vectors are linearly independent. So this means you can set up, say this can be linear equations. So you have alpha 1 multiplied by this one. I'm picking the first row. So I will have alpha 1 plus alpha 2 times 0 will give me 0. And then alpha 3 times 0 also gives me 0. So this is supposed to be equal to, using the first entries in each vector, I can create this equation. Now the second one will give me 2 alpha 1 plus alpha 2. And alpha 3 times 0 will give me 0. So this last one is 0. And this should be equal to the second slot in the vector on my right hand side. They're all 0, so that will also be 0. Then the last one is what? 3 alpha 1 plus 0 plus alpha 3. All this is equal to 0. So now we need to solve this set of equations. And if the only solution we can find is that all the alpha 1, alpha 2, and alpha 3 are 0, that's the only solution, then we conclude that this set of vectors is linearly independent. So let's check. We have an easy place to start from. This first one simply gives us alpha 1 is equal to 0, right? So now that we know alpha 1, we can substitute it in the second equation to give us alpha 2 equal to 0. Because if alpha 1 is 0, the only way you can get 0 on this side is if alpha 2 is equal to 0. So again, we come to the conclusion that alpha 2 is 0. Similarly, we already know alpha 1 from the first equation. We substitute 0 here, and that means that alpha 3 must also be. So Now, the only solution we can find is that alpha 1, alpha 2, and alpha 3 must all be 0 for this equation to be satisfied. Now, that leads us to the conclusion that the vectors 1, 2, 3, 0, 1, 0, and 0, 0, 1 are linearly independent. That makes sense? So that's now applying this definition to show that a set of vectors is linearly dependent. You can apply this to a larger set of vectors and in a larger Euclidean space, n-dimensional, where n is some positive integer. And we might see some of those examples later. For now, we're trying to just run through the basics, build up the tools of trade, then we shall hopefully.
Dr. Ali,
Yes.
in this example, isn't it supposed to be 0AB instead of 0A1? No. Go to the slide.
Let's hold on. What have I done?
Yes.
What?
I'm talking about the answer 0A1. This is supposed to be B because
Should be
B
B.
times 1 is B.
You're right. Yeah, this is a mistake. It should be B. But what matters is the first one. You have a contradiction already. This should be B. You're right. The contradiction comes from the first entry. You have 1 equals to 0, which is not. Yeah.
And then I have a question. I might have joined late. Maybe you've explained. I don't know. What are we looking at? What is the bigger picture by understanding the dependence or independence of the of these linear combinations?
What I will do, I will ask you to only do one thing at a time. Don't walk and chew at the same time. In this case, let's just walk, okay? We will chew later. It is for now, you cannot use what you don't know. So let's learn it first. We have several more classes. We shall use this linear independence and dependence a lot. So I don't want to mix the two. You will have plenty of uses for this as we go along. Don't worry. For now, I don't want to mix them. There's this tendency to always want to jump to applications, but my policy is you cannot apply what you do not know. So let's learn it first and we'll apply it. So the next concept that we are going to work with is this concept of basis and dimension. So we'll start with let's pick these two vectors. There's the two vectors. The first one we'll call it U, the second one V. So this is 1, 0 and 0, 1 in R2. Now, if I pick the vector 3, 5, then I can write this vector 3, 5 as a linear combination of U, V as follows. I will multiply 3 by U and 5 by V. Right? So this is just an example of any vector in R2. So in general, if I pick a vector in R2, it's possible for me to write that vector as a linear combination of U and V. Right? So any vector, based on this setup here, we can see that it doesn't matter what the value of A and B is, it's always possible to write a vector AB as a linear combination of 1, 0, the vector 1, 0, and the vector 0, 1, with the scalars used being A for 1, 0 and B for 0, 1. So this is always possible. It doesn't matter which vector in R2 that you pick, this will always be possible. And what that means is that any vector in R2 can be written as a linear combination of the vectors U and V. So if that is possible, if I have a pair of vectors, in this case, it's a pair, and I'm able to write any set of vectors in R2 in this case, as a linear combination of that pair of vectors, then we will say that this pair of vectors spans R2. It spans. So the key word here is a span. So these two vectors, U and V, they span R2. Now, you may observe that if you wish, that U and V are also linearly independent. We shall make some formal definitions later. So this set UV is called the standard basis for R2. We shall also get a formal definition of a basis, but for now we're just picking some concrete stuff as we go along. So these two vectors, 1, 0, and 0, 1, are called the standard basis for the space R2.
Yes, doctor, you can let someone in.
Okay. There's someone whose microphone is on and they're speaking.
Oh, finally.
I don't know whose microphone is on. Maybe try to switch off your microphones. So in general, oh, okay, let me find this person and mute them. He's called Batirum. So now let's go to this last remark. So this remark says that if you pick any two linearly dependent vectors in R2, they will form a basis for R2, right? So the keyword is this basis. And then there are two things you need to pick up from here. When a set of vectors spans a vector space, and then there's this standard basis for R2. So keep track of that. We shall keep referring to that. So in general, if I have any two linearly independent vectors in R2, they will form a basis for R2. We'll eventually define a basis in a formal way. For now, just accept that. So we have a set of definitions here we shall look at. So if you have a set of vectors in a space V, it is said to span that vector space. If any other vector in V can be written as a linear combination of the vectors in the set. So we have looked at an example of two vectors in R2, and any other vector in R2 can be written as a linear combination of the vectors, the two vectors in the set that we looked at. You can extend this to any vector space. So now we will also define what's a basis. So if you have a vector space, and when we say vector space, in our case, we shall mean Rn, Euclidean n space. Any set of vectors in V is a basis for V if it satisfies two conditions. One, it must be linearly independent. So that set of vectors must be linearly independent. And two, it must span V. In other words, any other vector in V can be written as a linear combination of that of the vectors in that set. So most of the time we shall be working with R2 and R3. You can work with larger spaces if you wish. And when you're working with data, most of the time you will work with very large spaces. R2 and R3 will just be for illustrative purposes, but when working with data, this n can be as big as 10 billion. But you don't need to the important thing is that what works for 2 works also for 10 billion. So once we learn what is happening with 2 or 3, we can extend the ideas to any dimension. So now, if once you have a basis, any basis for a given vector space will have the same number of elements. So that number of elements in a basis is what we call the dimension of the vector space. So for example, in R2, we found a basis consisting of the vectors 1, 0, and 0, 1, and there are only 2 vectors. They are linearly independent. So we say that the dimension of R2 is 2, since any basis will have exactly 2 vectors. That will be true for R3 and Rn as we go on. Let's see what we have next. We'll look at some examples. So if you have, let's look for a second, a different pair of vectors in R2. Previously, we saw the standard basis consisting of 1, 0, and 0, 1. So now let's pick another pair of linearly independent vectors in R2. In this case, we'll pick 1, 0, and 1, 1. Then we pick any an arbitrary vector in R2 with the entries A, B. So it can be shown that any vector AB in R2 can be written as a linear combination of 1, 0 and 1, 1, where the coefficients are as follows. For 1, 0, the coefficient is A minus B. And for 1, 1, the coefficient is B. This is something you can solve and confirm. So this means that given any vector in R2, you can express the vector as a linear combination of these 2 vectors, 1, 0 and 1, 1. And therefore, this set of vectors, U and V, spans R2. Now, this set of vectors is also linearly independent. Again, you can confirm that because we cannot write U as a multiple of V. It's not possible. And therefore, it satisfies the 2 requirements to be a basis. It spans the set R2 or the vector space R2 because you can write any vector as linear combination of these 2 vectors. It is also linearly independent, this set, and therefore we call it a basis of R2. So you can get many different bases. All you need to get a basis for R2 is to find 2 vectors in R2 that are linearly independent. That will give you a basis for R2. There's a lot more theory that can justify this, but I'm trying to focus on just the bare minimum, what you need to move forward. So as an example of how to use these 2, let's go back to the formula. You can see if you have AB, if you want to write AB as a linear combination of 1, 0 and 1, 1, the claim here is that the coefficients for 1, 0 will be A minus B, and the coefficient for 1, 1 will be B. And this linear combination should give you AB. Let's just check that directly using an example. So for instance, if A is 5 and B is 3, you can write 5, 3 as a linear combination of 1, 0 and 1, 1 as follows. Take the coefficient for 1, 0 to be 5 minus 3. That was A minus B in our workings before. And then the coefficient for 1, 1 should be B. In this case, B is 3. So if you work this out, you should be able to confirm that you get the same answer. So if you multiply 2 times 1 plus 3, we'll get 5. And 2 times 0 plus 3, we'll get 3. So this linear combination is correct. There's similar, we apply it to another example here. So there's nothing new. We're just applying the same formula to another example. But what we are applying is this result to a specific example just to illustrate that it works. So this is not a proof that this is true. You can actually do some analytical solution to this to prove that it is true. You're just solving a system of simultaneous equations in 2 variables. So This is something you can do. You did this in high school, so maybe not in high school, but at least first year mathematics, depending on. No, high school, yes, you did simultaneous equations in two variables. So this is you should be able to solve this. Now, so one more example. So this set 2, 7, this vector set of vectors 2, 7, and 1, 5 is actually a linearly independent set. You can confirm that because it's not possible to write 2, 7 as a multiple of 1, 5. So this set is linearly independent, and therefore must be a basis for R2. That's what we said earlier. If you find any pair of linearly independent vectors in R2, they form a basis. So you can check that that is the case because any vector in R2, any vector in R2, in this case, AB is a vector in R2, can be written as a linear combination of 2, 7 and 1, 5. And the corresponding coefficients will be obtained as 5 over 3A minus 1 over 3B for 2, 7 and minus 7 over 3A plus 2 over 3B for 1, 5. So you can check this on your own letter and confirm. My mouse is jumping. I think now it's stable. So you can check this on your own letter. That this actually holds. You can test it with an example. So here is an example. Actually, you can try to work this out on your own. So I propose we take a 5-minute break. Is that okay? Or you are you have the momentum now. We should keep going. You can hear me? Oh dear.
Yeah, we can have a 5-minute break.
Okay, so we resume at 10 past 8. I think we can resume now. Hopefully by now you've had a chance to check that this follows works. In the next slide, we're just applying this solution to an example. You can check this in your own time and confirm that it works. So I'll move to the next. I think it's the last thing we shall look at today. And that is the concept of coordinates. So for now, we are focusing on two-dimensional space because it's easier to illustrate with this, but all these ideas can be extended to any dimension. So if you're given a vector in R2, it's possible to get many different bases. And for each of these bases, it's possible for you to write that vector as a linear combination of the vectors in the basis. So we'll start with an example. Here is an example. We have the vector 6, 9. You are going to write the same vector in 3 different ways using 3 different bases. These are all bases we have considered before. So the first basis we shall look at is a basis consisting of the vectors 1, 0 and 0, 1. Earlier on, we saw it's possible to write any vector in R2 as a linear combination of these 2 vectors. So 6, 9 can be written as 6 times 1, 0 plus 9 times 0, 1. And then the same 6, 9 can also be written as minus 3 times 1, 0 plus 9 times 1, 1. And again, the same 6, 9 can be written as 7 times 2, 7 plus negative 8 times 1, 5. Is that correct? I think it's correct here. So you observe the following. For each set of each basis, we have different scalars. So for the first basis, the scalars here we have 6 and 9. For the second basis, the scalars you need are negative 3 and 9. And then for the third basis, the scalars you need 7 and negative 8. So you can see the code, depending on the basis, the coordinates keep changing. Or rather, these scalars keep changing. So these scalars are normally called the coordinates. So for instance, the coordinates of 6, 9 with respect to this standard basis is just 6, 9. Right? But when you change the basis, the coordinates of 6, 9 now with respect to this second basis will be negative 3, 9. And for the same 6, 9, it changes the coefficients again if you change the basis. And now the new coordinates will be 7 and negative 8. So these coefficients are called the coordinates. So we will now define the coordinates of a vector. So if you have any pair of vectors, u and v in R2, and they form a basis. This is a pair of vectors that form a basis. If you pick any other vector in R2, because it's a basis, it's always possible to express that vector as a linear combination of the 2 vectors in the basis. Now, these 2 numbers, a and b, that you will satisfy this equation are called the coordinates of the vector w with respect to this basis consisting of vectors u and v. So the keyword is coordinates with respect to a given basis. And as you change the basis, the coordinates change. Are we together? So for example,
yes,
here, good. So this just repeats what I just talked about earlier, but it does now put it in a compact form. So for instance, here you have 3 bases. You have one basis B1, a second basis B2, and a third basis B3. And earlier on, we picked out the coordinates for the vector 6, 9 with respect to the three different bases, B1, B2, and B3. So when you're working with the standard basis, the coordinates usually will simply be the same entries in the vector. So for the standard basis, the coordinates usually coincide with the vector itself. But for other bases, different from the standard basis, the coordinates will not necessarily be the same as the elements in the vector. As you can see for these two other examples, the coordinates are not the same as the elements in the vector. So this change of coordinates is used a lot in data science. Many times you do transformations and you have to work with a new set of coordinates. And an example where you do this is when you're working with the principal components analysis. It's basically changing coordinates, changing bases rather. Then you work with a new set of coordinates. We'll deal with that in detail when we get there. So now we've been looking at examples in R3. Let's look at in R2, sorry. So let's look at a few more examples in R3. The same ideas, but now extended to R3. And of course, they can be extended to R4, R5, or R1 million. It doesn't matter. The ideas, they extend quite naturally to larger spaces. But because it's easier to illustrate with the smaller spaces, we work with the smaller spaces for now. So this one says, consider the following basis for R3. So this is a basis for R3. For now, you'll just have to believe that this set of vectors is linearly independent and also spans R3. In other words, any. So if you pick any vector ABC in R3, you can show that this is how you can express it as a linear combination of these vectors in the basis. So now the coordinates for this vector ABC with respect to this basis will be A minus C, A minus B minus C, and then plus C. So as an example, if you pick the vector 2, 7, 3 and apply the results on it, you'll find that the coordinates for 2, 7, 3 with respect to this basis will be -1, -8, and 3. So these are the coordinates of the vector U with respect to this basis for R3. This is a basis, and the coordinates are obtained here. These are the coordinates. Now, the number of vectors in any basis for R3 will always be equal to 3. It doesn't change. And that is also what we'll call the dimension of R3. R3 has dimension 3 because any basis for R3 will have exactly 3 vectors. So all these statements I'm making are not trivial. They can be proved using a lot of algebra. For now, the important thing is what I have said, that any basis in R3 will have exactly 3 vectors. And therefore its dimension is 3. So most of the time we shall talk of ordered basis. An ordered basis means you can choose an order. So you can choose this to be the first vector in your basis, this one to be the second vector in your basis, and that as a third vector in your basis. So anytime you refer to this as a basis, you work with them in that order. The reason for that is sometimes you're interested in the coordinates. And if you switch the order of the elements in the basis, the coordinates will be different again. They will switch. So for consistency, anytime you pick a basis, we stick with the order or fix an order and stick with it, so that we have a vector that will always be act as the first one in the basis, another one as the second, another one as the third. You can reorder them in any way, but once you pick the order, you need to stick with that so that you have consistency when you're computing the coordinates. So that is what this remark explains. So we'll try to extend this to a more general case. So if I have a set of vectors, v1, v2 up to vn of n linearly independent vectors in Rn, they will form a basis for Rn. So throughout, we are assuming we are working with either R1, R2, R2 or R3 or Rn. Rn is now the general case. So if you have a basis for Rn, it will always like this. Or rather, any set of n linearly independent vectors in Rn will form a basis for Rn. Again, this can be proved with a lot of theory, but then we won't do anything else in the class if we work with the theory. Then for that reason, we say the dimension of Rn is n. For now, just take this as a gospel truth. If you have any linearly independent, any set of n linearly independent vectors in Rn, they will form a basis. In other words, any other vector in Rn can be written as a linear combination of the vectors in that set. So once you have a basis, you retain the order. So you have v1, v2 up to vn. So you have the ordered basis. If you have any other vector in Rn, because it's a basis, it should be possible to write it as a linear combination of the vectors in the basis for Rn. Now these coefficients, alpha 1 up to alpha n, are what we call the coordinates of u with respect to the basis, given basis. Now these coordinates are unique. In other words, if once you fix the basis and the order, each vector will have a unique set of coordinates. You can't have a vector that has more than one set of coordinates. Each vector has a unique set of coordinates. Again, that can be proved, but we are not going into the linear algebra in depth. So if you want to see the details of this, the textbooks I shared will cover this. And you may follow up with questions later if you read and you don't understand. So the important thing is this: you have a basis. In other words, for the set Rn or the vector space Rn, any set of n linearly independent. So for instance, if n is 10, these vectors must be 10 and they must be linearly independent. And as long as they are linearly independent, they will form a basis for Rn. And therefore the dimension for Rn must be n. And once you have a basis, by definition, it is possible to write any other vector as a linear combination of the vectors in this basis. And that linear combination is given here. Once you figure out this linear combination, then the coordinates will be this list of coefficients. So usually write the coordinates as a scalar. Again, it's ordered in the order, the coefficients are ordered in the same order as the vectors in the basis. So another observation we'll make, which we already made when working with R2, is if you use a standard basis, then the coordinates of the vector are the same as the components of the vectors. So there are some bases that are better than others. So later on, we'll try to see what makes some bases better than others. And that's why, for instance, when working with the principal components analysis, you change the basis to use a more convenient basis. Usually, by changing the basis, sometimes you can solve a lot of problems. So there's a certain class basis known as orthonormal basis, and they can be very convenient. We shall learn about orthonormal basis later. It takes quite a bit of work to compute them. For now, just
maybe just a confirmation.
Yes.
With regard to the equation you said, so is this coordinate making it to be linear dependent? I mean, making we have here B, but we have those values V1 to Vn, which are obviously linearly independent. So when we use the U where we now have the alpha, we involve the coordinate. Is it now making it more of kind of linear independent?
When you talk of linear independence, you need to talk of a set. So you need a set of vectors.
Yes.
Let's go back to the definition. You need a set of vectors. So it's really important to keep track of these definitions. Where's linear? We just need one of them. So we need a set of vectors. So for example, here is you're talking of dependence, so we can go back to dependence. So you need a set of vectors. The first example we picked was R2. So we have two vectors. And for two vectors to be linearly dependent, you just need to show that one is a multiple of the other. So that's easy. But now you say that set of vectors is linearly dependent. Okay?
Yes.
So good. So you can extend this to the general case. If you have R vectors, they're linearly dependent if you can find scalars whereas not all of them are zero, such that this equation is satisfied. You can see what I have here is zero, the zero vector. Then I have a linear combination of the remaining vectors. And if this equation is satisfied and some of the scalars I use are not zero, then we say that these vectors are linearly independent. Right? Linearly dependent, sorry.
Dependent.
Yes. So now what you are talking about is two different things. So when you're talking of linear dependence or independence, you start with a set of vectors. You don't work with an equation. You start with a set of vectors, then you show that that set of vectors is linearly dependent if it satisfies that expression where all the linear combination equals zero, the zero vector, and some of the constants are not zero. So here we have already determined that this set of vectors is linearly independent.
Yeah.
Here U is not considered as part of this set.
Yeah.
U is just a different vector. So what we're interested in is writing U as a linear combination of the other n vectors. Now, if I want to talk of them being linearly dependent, I need to pick a set. I don't talk of U separately or the other set separately. So if I add U now if I add U to this set, then it becomes linearly dependent. Because now U can be written as a linear combination of the other vectors. So if I add U to this set B, then that set becomes linearly dependent. So anytime you're talking of linear dependence or independence, you focus on a set of vectors. And that set of vectors is linearly dependent or independent.
All right.
So these are just remarks. And this last one captures, I think, what you're saying. If you have a basis which is a set of linearly independent vectors, by just adding one more vector to the basis, it will no longer be linearly independent. It will be linearly dependent now. So the example we have here is, the reason it will be is because any vector you pick in Rn can be written as a linear combination of this. So if you pick any other vector and add to this set, then it's no longer independent. And that's what this last remark says. Adding one or more vectors to a basis makes a linearly dependent set. And now if we exclude by just removing one vector from the basis, then it fails. It will still be linearly independent. The new set after removing one vector, or even more than one vector from a basis, the new set will still be linearly independent. But now it will no longer be, it will no longer span the vector space. It will not be, there will be some vectors which cannot be written as a linear combination of the remaining vectors. We can give an example here. For instance, the simplest example, but maybe too simple and misleading, is this one. So for instance, if I have a basis 1, 0 for R2 consisting of these standard basis vectors. So this is a set that consists of these two vectors that form the standard basis. If I create a new set consisting of only 1, 0, then I've knocked out one vector from the basis. So now I have only 1, 0. While I'm here, it's always possible. For instance, if I pick a vector like 2, 3, I can always write it as a linear combination of my basis vectors 1, 0 and 3 times 0, 1. Now, but if I move to the other side, the same vector now is 2, 3. Once I drop one vector from the basis, I can no longer write 2, 3 as a linear combination of, in this case, as a multiple. This is not solvable. There's no number which will satisfy this. I can't find such a number. So this now no longer spans R2. Once you drop just one vector, then the new set you end up with will not be a basis because it does not span R2. Remember, basis must be linearly independent and must span. Span means any vector in the vector space can be written as a linear combination of the basis vectors. So now you still have a linearly independent set, but it no longer spans, and therefore it fails to be a basis now. So this last remark says, by dropping just one alone, dropping just one vector from a basis stops it from being a basis. It no longer spans the vector space. So this will illustrate that, and then maybe you can try something more dramatic. So you can write this down and later on try. So this set of vectors will form a basis. So there's 1, 0, 1, 1, 1, 0, and 0, 1, 1. I think this will form a basis for R3. This is a set of 3 linearly independent vectors, and any 3 linearly independent vectors in R3 will form a basis. So maybe you can call this first one U, this second one call it V, and this last one call it W. So your exercise is to pick any vector in R3 and find some scalars. I'll call the first scalar alpha 1 multiplied by 1, 0, 1. The second scalar, we'll call it alpha 2. My handwriting, this mouse is hard to write with. 1, 1, 0. And the last one is alpha 3. and 0, 1, 1. So your work is to find these scalars. For any vector in R3, you need to find the scalars alpha 1, alpha 2, and alpha 3 that will satisfy. So these scalars alpha 1, alpha 2, and alpha 3, you should write them in terms of A, B, and C. So try to solve this in time. Since the vectors are, so then the next thing you will do, drop one of the vectors. So let's just stick to the first two. 1, 0, 1. So we have 1. So we create a new set, but this new set drops one of the vectors. In the particular, we drop the last vector. We can drop any, and we still have the same effect of stopping this from being a basis. So now here is a new set. So your challenge now for this second set, can you find a vector? Now a new vector, you can find actual numbers in this case. Find numbers and replace A, B, and C with numbers so that this new vector should not be possible to write it as a linear combination of. It's not possible to find such vectors alpha 1 and alpha 2 and make, let's use alpha 2 and 1, 1, 0. So now your exercise is to find a vector. In this case, A, B, and C, you should find actual numbers like I did for the case of R2. Find a vector which cannot be written as a linear combination of these two remaining vectors. We have dropped one vector from the basis, and then the remaining vectors here show that you can find some vectors which cannot be written as a linear combination of these two vectors. Maybe as a hint, you should try a vector like 0, 1, 2. You can show that this vector 0, 1, 2 cannot be written as a linear combination of this and that one. So this will illustrate the ideas that if you have a basis, by just dropping one vector from the basis, it fails to be a basis. That means it doesn't span the space anymore, as I've tried to illustrate using this. But if it is a basis, it is a set of 3 linearly independent vectors in R3, and therefore must be a basis. And since it is a basis, it should always, if you work with a full basis, it should always be possible to find these scalars that will satisfy this equation. So that's your exercise. I think you will do that and report back to me in the next class. The next topic we need to work on is subspaces. All these things are applicable, but we cannot do everything at the same time. We have to first learn the ideas, then we can apply them. And there's no shortage of applications. So the next thing we shall look at are subspaces. I believe we can stop the class there for today.
Daktari, I have a question.
Yes.
I've noticed that you've given us different bases for the exercises compared to the bases that are given in the coordinates. Should we use them as they are, or?
I don't understand.
Oh, I'm saying the bases that you've given us for the exercise. These 101, 110, and 011.
Yes.
They are different from the ones that have been given in the slides.
Yes.
So should we use this one as they are, or we regard it as a mistake? Because the ones given in the coordinates.
Why do you want them to be the same?
It may make it easy